Imagine, a stadium-sized asteroid is going to hit Earth in 2 weeks. Even at this moderate size, a fireball brighter than the sun tears through the atmosphere at 60 times the speed of sound, and the destructive power of 4,000 Hiroshima bombs flattens cities, killing millions. The heat from that fireball would be so intense that it would ignite forests hundreds of miles away before the shockwave even arrived. The ground would shake like never before. The sky would turn white, then red, then black. This isn't science fiction. Many killer asteroids were only spotted at the last moment. In 2019, asteroid OK, as big as a 30-story building, was discovered just one day before it grazed Earth closer than some of our satellites. Think about that for a second. We have satellites that orbit our planet for years, and this giant rock flew right past them, and we only noticed it the day before. Last year, the even larger asteroid MK was spotted 13 days before it passed us closer than the moon. That is less than 2 weeks of warning for an object large enough to wipe out an entire country. If they had hit Earth, they would have unleashed the destructive power of 3,000 and 9,000 Hiroshima bombs. Stunningly enough, humanity doesn't really have a plan for this. We have no planetary defense system. No giant cannons. No shield. Nothing. Scientists have devised all kinds of tricks to push dangerous asteroids away. Painting it so sunlight will deflect it over many years. Landing thrusters to steer it like a cosmic tugboat. Scorching it with lasers to vaporize part of its surface and create a tiny push, or even crashing spacecraft into it to change its orbit just a little bit. But they all have a big problem. They are the equivalent of trying to deflect a cargo ship by throwing a bag of potatoes at it. They do move the asteroid, but only by a tiny, almost laughable amount. With these methods, you need to act years or even decades in advance to make an asteroid miss the Earth. You need to find the asteroid when it is still far beyond Jupiter, and then gently nudge it, so that years later, it passes safely by. But what if you find it late? What if you only have weeks? Then these gentle methods are useless. They simply cannot change the asteroid's path enough in such a short time. But very recently, scientists have developed a new spectacular way to destroy killer asteroids that we could implement with today's technology. Not in 100 years. Not with futuristic lasers or space magic. Right now. With rockets that already exist and physics we already understand. Let's see how this works with our 100-meter asteroid heading for Earth. The secret weakness of asteroids. For a long time, people imagined asteroids as being gigantic stones. Solid, hard, like a flying mountain made of rock and metal. But it turns out most of them aren't like that at all. We have sent probes to asteroids. We have landed on them. And what we found surprised everyone. They are more like bags of loosely packed gravel. Heaps of pebbles, precious minerals, and dust barely held together by their own weak gravity. You could almost think of them as cosmic piles of rubble. If you punched one, your fist might go right through. If you crashed into one, it would not crack like a boulder. It would crumble like a sandcastle. Which means that instead of just nudging them, we can do something better. Pulverize them. You don't nudge a pile of sand, you blow it apart. And the obvious choice is, of course, a nuke. It is the most powerful explosive we have. It is the classic Hollywood solution. So, let's go. We load up a nuclear warhead, launch, aim at our deadly asteroid, and... oh. The asteroid destroyed the nuke. Asteroids can approach Earth at 70,000 kilometers per hour, enough to cross the Atlantic Ocean in 5 minutes. At that speed, the asteroid is essentially a bullet made of rock, and our nuclear missile is a fragile tube of metal and electronics. When they meet, the asteroid wins every time. No bomb we've ever made could survive such an impact. The electronics would be smashed. The casing would be torn apart. The nuclear material would be scattered into space. So if we go for a head-on collision, the asteroid will wreck the nuke before it even has a chance to explode. Okay, easy. Let's explode the bomb before it touches the asteroid. Scientists have estimated the optimal distance, which for our 100-meter killer friend would be a few tens of meters above the surface. That way, the nuke doesn't have to hit anything. It just has to get close and then detonate. Launch, set the timer, and sad boom. The explosion has made a dramatic crater on the asteroid's surface and nothing else. A flash of light. Some radiation. But the asteroid keeps coming. Unfortunately, in space, there is no air to carry a shockwave. On Earth, a nuclear explosion creates a massive wall of compressed air that flattens buildings for miles. In space, there is no air. So most of the explosion's energy is lost as harmless light and heat. The rock will still hit us in 2 weeks, only a few kilometers to the left of where it would have hit before. That is not enough. A few kilometers is nothing when the fireball is dozens of kilometers wide. Striking such a behemoth with a nuke is like hitting our cargo ship with a washing machine instead of potatoes. Better, but still useless. Okay, let's go the movie route. Land someone on the asteroid, drill a hole, and bury a nuke inside to avoid all of these problems. That way, the explosion is contained inside the rock. The energy has nowhere to go but out, ripping the asteroid apart from within. And indeed, this is possible in theory, albeit suicidal in practice. Landing on any space body is a nightmare. Even on fairly big Mars, whose surface we know almost perfectly, roughly 70% of our landing attempts have failed. Landers crash, parachutes tangle, engines misfire, and that is on a planet with an atmosphere and a solid, predictable surface. So imagine the chances of landing a crew and a nuclear bomb on a small and extremely fast asteroid discovered just 2 weeks in advance. The asteroid would be tumbling. There would be no gravity to hold you down. One wrong step, and you would float away forever. Even if we succeeded, drilling in microgravity is painfully slow, since there is no downward pull to help you. On Earth, a drill works because gravity pushes the bit into the rock. In space, the drill just pushes the asteroid away. You would need special clamps and anchors, and hours of careful work. So, we would need an agonizing amount of time that we don't have. 2 weeks is nothing. By the time you launched the rocket, traveled to the asteroid, landed, drilled, planted the bomb, and flew away, the asteroid would already be hitting the atmosphere. So sadly, that's not the answer. We have to think less like Hollywood and more like a lumberjack. The smart way. If you want to split a log, you don't hit it with a rock. That would just make a dent. You use an axe, a dense and perfectly shaped tool designed to concentrate all your force into a single sharp edge. And just in the same way, scientists have found a new tool to destroy asteroids. Super dense, ultra-fast, cosmic bullets. We won't even have to shoot them. That is the clever part. Our cosmic bullets are called penetrators. They are a few meters long, slim, and made of tungsten, a metal way denser and harder than rock. Tungsten is so dense that a small rod of it weighs as much as a car. It is also incredibly strong. It does not bend or break easily. These penetrators are designed to survive impacts that would vaporize anything else. They work in an extremely simple way. You just put the penetrators in the way of the asteroid to float silently in space. You don't fire them. You don't accelerate them. You just place them there like a cosmic speed bump. From the perspective of the asteroid, you wouldn't see a few tiny bullets sitting still. Because of relativity, from the asteroid's point of view, it is standing still, and the bullets are moving. You would see them rushing at you at 70,000 kilometers per hour. It doesn't matter who stands still and who is fast. All that matters is the relative speed between them. And that speed is enormous. But this speed means that by far the longest part of this mission is to get to the asteroid in time. We have to launch our rocket quickly. We have to travel millions of kilometers. And we have to do it before the asteroid gets too close. We can't destroy it too close to Earth because its fragments will slam into the atmosphere all at once with the power of thousands of nuclear bombs. Imagine a shotgun blast of rocks, all hitting the atmosphere at the same time. Each rock creates its own fireball. Each fireball creates its own shockwave. And if they all hit together, those shockwaves will combine into one giant wave of destruction. Our atmosphere can absorb isolated chunks. Small rocks burn up every night as shooting stars. But if thousands of them strike together, their shockwaves will add up and kill millions. So instead, we need to intercept it one day before impact, when the asteroid will be nearly 2 million kilometers away, more than 4 times further than the Moon. That is a vast distance. You could fit all the planets of the solar system between Earth and that asteroid. But it is doable. Our current rockets can cover this distance in about a week. We'll send just one penetrator, about 2 meters long and weighing 2.5 tons. That is about the size of a telephone pole, but much heavier. Once our rocket arrives, it puts the penetrator in place to cause maximum damage. It calculates the exact point of impact. It aims for the center of mass. And then we wait. For hours, nothing happens. Then, a tiny speck of light appears in the vast distance. It grows slowly at first, then faster and faster. And then suddenly it's here, shooting at us faster than the speed of sound. There is no time to react. No time to blink. We'll slow down time to see exactly what happens. The asteroid crashes into the penetrator so fast and with so much violence that the power of 120 metric tons of TNT is released into the asteroid. That is a large bomb. Not a nuclear bomb, but a very large conventional one. All of that energy is focused into a single point, no bigger than a coin. The rock at that point doesn't crack. It doesn't break. It vaporizes instantly. It turns into plasma, a hot gas of atoms. The tungsten melts away, but not before it has punched deep into the asteroid. The penetrator carves a wound that tunnels through the asteroid like a hot needle through butter. The damage is too much. The asteroid is a rubble pile, remember. It is barely held together by gravity. And now, with a tunnel of vaporized rock running through its core, with all of this energy looking for a place to go, the asteroid simply cannot hold itself together. It explodes, not like a bomb, but like a sandcastle hit by a wave. The asteroid is blasted into thousands of pieces. Some pieces are as big as houses. Most are as small as pebbles. The debris spreads out into a diffuse cloud, expanding outward in all directions. A day later, the fragments hit Earth, but they are no longer a single bullet. They are a cloud of dust and gravel, dispersed over hundreds of thousands of square kilometers. Instead of one massive fireball, we get thousands of beautiful shooting stars. Instead of a continent-shattering impact, we get a mostly harmless show of cosmic fireworks. The apocalypse becomes a light show. So if we prepare and get everything ready, spotting a killer asteroid with 2 weeks' notice would be enough. We could survive. We could win. But this was just a small asteroid, 100 meters across. That is the size of a stadium. That is dangerous, but it is not the end of the world. What if we face a cosmic mountain, a planet killer, carrying the destructive power of tens of thousands of nuclear arsenals? The non-avian dinosaurs would tell you about it, but they're dead. 66 million years ago, a planet killer the size of Mount Everest hit Earth. It did not just kill the dinosaurs, it killed 75% of all species on the planet. The sky turned dark for years. The oceans acidified. The forests burned. That is what a planet killer does. What if it is a planet killer? Planet killers are objects so vast and powerful that they would end most life on Earth in a single strike. The most dangerous ones are comets from the outer fringes of the solar system. These comets are so distant and dark that tracking them is impossible. We don't see them until they are already inside the orbit of Jupiter. Sometimes we don't see them until they are inside the orbit of Earth. Comets are dirty ice balls the size of mountains. They are more fragile than pure rock because they are made of frozen gas and dust, but they are also much faster and more violent, traveling at around 140,000 kilometers per hour. That is twice as fast as a typical asteroid. In 2020, the comet Neowise, with the power of 6,000 times all the nuclear bombs on Earth, was discovered just 4 months before its closest approach to Earth. 4 months. That is 120 days. If that comet had been aimed directly at us, we would have had 4 months to figure out how to stop a mountain of ice moving at twice the speed of a bullet. What if we find such a beast 6 months before it's going to crash into Earth? Do we have a chance of surviving this? Unfortunately, this would be extremely hard for a bunch of reasons. First of all, our planet killer comet has so much more mass than a tiny killer asteroid. A 100-meter asteroid weighs maybe 2 million tons. A planet killer comet weighs billions of tons. It is thousands of times more massive. so simply breaking it into millions of pieces would not help us that much. Each piece would still be huge. The chunks that hit Earth would still be massive and numerous enough to set the sky ablaze and kill most life on Earth. You cannot just pulverize a mountain and expect the gravel to burn up in the atmosphere. The gravel would be the size of houses. Houses do not burn up. They hit the ground, so we need to make most if not all of its fragments completely miss Earth. We need to change its path, not just break it apart. But to do that, we need to destroy it much further away. Much, much further away. We need to intercept it at the distance of Mars, or even beyond. Because if we break it close to Earth, the fragments will still hit us. Gravity will pull them in. We need to break it so far away that the fragments spread out and miss our planet entirely. That means traveling hundreds of millions of kilometers. And to destroy a mountain, we need way more penetrators. Not one, not 5, hundreds of thousands. Each penetrator can only vaporize a small amount of rock. To destroy a mountain, you need to hit it again and again and again in the same spot until you drill a hole deep enough to crack it open. That takes an enormous number of penetrators. And this is, well, a huge problem. To travel this far and to transport this much payload, we need at least 24,000 super heavy rockets. These are rockets like the Saturn V that took astronauts to the moon, or the SpaceX Starship. Each rocket can carry maybe 100 tons of penetrators. To carry hundreds of thousands of penetrators, you need tens of thousands of rockets. As of today, humanity has 2. And they are not really finished yet. The SLS has flown once. The Starship has exploded a few times. Even if all the industries in the world do nothing but switch to building rockets, we would not finish in time. It would take years to build 24,000 rockets. We have 6 months. If we actually discovered a planet killer today, there is literally nothing we could do about it. We would have to accept that most life on Earth would die. Except, maybe if we combine penetrators with a bit of Hollywood and our old friend, the nuclear bomb, there is still a way. A single nuclear bomb is useless against an asteroid if it explodes on the surface. But if you can bury it deep inside, it becomes incredibly powerful. The problem has always been how to bury it without landing and drilling. But what if you could use penetrators to drill the hole for you? What if you fire a series of tungsten rods into the comet, each one hitting the exact same spot, deeper and deeper, until you have a tunnel hundreds of meters deep? And then, instead of the last penetrator being a piece of tungsten, you send a nuclear bomb. It flies down the tunnel and explodes inside the comet. For this plan to work, we basically need to have all the parts ready beforehand. We cannot build the rockets after we find the comet. We have to have them waiting. A rocket like NASA's SLS, the one planned to take astronauts to the moon, loaded up with everything we need, ready to launch. It would sit on the launch pad for years, maybe decades, waiting for a threat that might never come. But if it does come, we are ready. As soon as the planet killer is spotted on its way to wipe us out, we launch a single rocket to meet it. Just one rocket. Not 24,000. One. For 5 long months, it travels through the nothingness of space as life on Earth nervously continues. People go to work, children go to school. But everyone knows what is coming. Everyone watches the news. The rocket is our only hope. Finally, it reaches its destination a bit beyond the orbit of Mars. The comet is still millions of kilometers away, but it is coming. Now we deploy 5 massive penetrators in sequence, one perfectly lined up 2 kilometers after the other. They are released from the rocket one by one. They drift into position. They are separated by exactly 2 kilometers. The timing has to be perfect. If they are too close, they will collide with each other. If they are too far apart, the comet will heal between impacts. The engineering challenge of aligning and timing this correctly is horrendous. It requires precision measured in microseconds. And we only have one attempt. There are no second chances. So, a few very brave astronauts go on this one-way trip to supervise the process, with no way home. They know they will not return to Earth. They know the comet might kill them, but they go anyway. Because if they don't, everyone dies. They sit in their small capsule, watching their instruments, making tiny adjustments to the trajectory. They have trained for this moment for years. Nervous hours pass as all of humanity watches the skies and screens. Billions of people hold their breath. And then, the moment comes. The icy mountain of death appears in full, a dark shape against the stars. It grows larger and larger, and then it is already here. There is no time to think. Slow down time again. The comet smashes into the first penetrator at 140,000 kilometers per hour, unleashing the power of 2,000 tons of TNT. Ice, rock, and tungsten liquefy in an instant, as the energy of the impact eats itself dozens of meters deep into the mountain. A crater forms. Vaporized ice explodes outward in a plume of gas. The first penetrator is gone, vaporized. But it has done its job. It has created a hole. Here is the second one, perfectly hitting the same spot, punching directly into the crater, smashing, melting, drilling deeper. The second penetrator adds its energy to the first. The crater grows. The tunnel gets deeper. The third and fourth penetrators repeat the process again, now smashing a tunnel about 100 meters deep. That is deep. That is the height of a 30-story building. But this time, this is just a scratch on the surface of the monster. The comet is enormous. 100 meters is nothing compared to a mountain. The comet is not really damaged yet. It is just wounded. It is angry. It keeps coming. And then comes the final penetrator and its toxic load. 300 megatons of nuclear warheads. That is 20,000 times more energy than the bomb that destroyed Hiroshima. It is the largest bomb ever built by humans, several times more powerful than the Tsar Bomba, the biggest nuke ever tested. It travels deep into the tunnel. It flies through the hole carved by the 4 tungsten penetrators. It reaches the end of the tunnel, 100 meters inside the comet. And just before it hits the end, it explodes. This time, the nuke works. Instead of hitting nothing in the vacuum of space, the energy of the explosion smashes into rock and gravel and ice. It has nowhere to go but outward. The walls of the tunnel contain the explosion for a fraction of a second, and in that fraction of a second, the energy is transferred to the comet. On top of vaporizing it from the inside, there is so much shock and push and punch that the entire comet shudders. Cracks spread across its surface like lightning. The core of the comet, billions of years old, turns into hot gas. The surface breaks apart. The frozen world dies from within, turning into a cloud of millions of fragments spreading in all directions. Humanity is saved. The fragments spread out. Most miss Earth entirely. The ones that do hit are small, burning up in the atmosphere as a spectacular meteor shower. The oceans rise a little. The temperature drops for a year or two. But civilization survives. Life survives. To make this happen in reality would take unprecedented planning and precision. It would require global cooperation. It would require nations that are now rivals to work together. It would require us to spend billions of dollars on something that might never be used. It would require brave astronauts to volunteer for a one-way mission into the darkness. And yet, it is possible. Not in a century with sci-fi technology. Not with warp drives or laser cannons or force fields. Just with the rockets, engineering, and knowledge we already have today. The only question is whether we will do it before we need it.